Have you ever stopped to consider the very air you breathe? We think of oxygen as a simple, life-giving gas produced by plants bathing in sunlight. It fills our lungs, powers our cells, and paints the sky blue. But what if I told you there's another side to oxygen? A hidden, mysterious form that operates in the shadows far from the sun's reach, an invisible force shaping life in the planet's most extreme environments. Scientists have given it a name that evokes the vast, unexplored cosmos. Dark oxygen. It sounds like something from a science fiction novel. But the reality is even more fascinating, a testament to the universe's boundless chemical creativity and our own ever-expanding quest for knowledge. Now let's be clear. It's not magic, and it doesn't lurk in haunted houses. Instead, it describes a phenomenon, a new way of thinking about how oxygen behaves. The oxygen we're familiar with is free-floating, available for any organism with the right biological tools to grab it from the air or water. Dark oxygen, however, is a different beast. It is oxygen that has been chemically bound or altered, often attached to minerals or reactive particles. In this state, it's not readily available, but under the right conditions, it can be released and used by life in places where free oxygen is completely absent. It's a hidden reservoir of life's essential fuel. Imagine a pantry stocked with canned goods. The food is there, preserved and ready, but you can't eat it until you have a can opener. Dark oxygen is like that canned food. It's locked away within the chemical structure of soil particles, deep-sea sediments, frozen ground. Normal biological processes can't access it, but certain specialized microbes, the unsung heroes of our planet's hidden ecosystems, have evolved the equivalent of a chemical can opener. They have developed unique metabolic pathways that allow them to pry this oxygen loose, using it to breathe and thrive in total darkness. This discovery forces us to reconsider the fundamental rules we thought governed where life could exist. This concept opens up a universe of possibilities. For centuries, we've linked complex life directly to sunlight through photosynthesis by consuming organisms that do. The discovery of dark oxygen shatters this simple narrative. It reveals a planetary life support system that operates independently of the sun's energy, a dark biological engine running deep within the Earth itself. It's a profound shift in our understanding, suggesting that the habitable zones of our own planet are far larger and more diverse than we ever imagined. So, where do we find this elusive dark oxygen? The search takes us not to the stars, but deep into the fabric of our own world, to places long considered barren and inhospitable. One of the most compelling examples lies right beneath our feet in the deep soil sediments of the Earth. Near the surface, the soil is aerated, teeming with organisms that breathe the same air we do. But as you dig deeper, the free oxygen disappears, replaced by a dense, anoxic environment. For years, we assumed life here would be slow and limited. Yet scientists have found thriving microbial communities in these depths, and dark oxygen appears to be one of their secrets to survival. Consider the vast frozen landscapes of the Arctic, Antarctic. Here, permafrost, ground frozen for thousands of years, locks away ancient organic matter, water, gases. Within this icy matrix, oxygen can be bound to minerals and other compounds. As global temperatures rise and permafrost begins to thaw, these hidden oxygen sources are exposed. Specialized microbes, awakening from their long slumber, can potentially access this dark oxygen. This process could kickstart a cascade of microbial activity, allowing microbes to decompose ancient carbon frozen for millennia, a process with big implications for our planet's climate. Then we dive into the abyss. The deep ocean, a realm of crushing pressure and eternal night. Sunlight penetrates only the first few hundred meters, leaving the vast majority of the ocean in darkness. Here in the cold, deep water and the silty ooze of the seafloor, free oxygen is scarce. Yet life persists. Bizarre fish, ecosystems of microbes. Dark oxygen, created when surface oxygen reacts with sinking particles and minerals, may be a key part of this story. In oxygen minimum zones, where life seems to struggle, microbes might tap chemically bound oxygen sources, creating an oasis of activity where we once saw a desert. These are not isolated curiosities, but examples of a fundamental planetary process we overlooked. It represents a hidden branch of the planet's respiratory system, one that doesn't rely on lungs or gills, but on the subtle, powerful language of chemistry. When we hear a term like dark oxygen, our imaginations can run wild. It's easy to fall into the trap of thinking it's something entirely new, a substance disconnected from the world we know. So let's perform a little cosmic clarification, a journey from myth to fact. The myth is that dark oxygen is a newly discovered element or a fundamentally different type of gas, perhaps like the dark matter we search for in the cosmos. It suggests a substance that follows its own set of physical laws, a shadow element that exists parallel to our own. This is a captivating idea, but it's not what the science tells us. The universe is elegant, and the explanation is often found within the rules we already understand. The fact is, far more subtle, and, in my opinion, far more beautiful. Dark oxygen is simply a new role for an old friend. It is still the element oxygen, the eighth element on the periodic table, the same stuff that makes up 21% of our atmosphere. The dark part of its name refers not to its nature but to its origin and state. It is produced and becomes available for life without the energy of sunlight. It is oxygen that has been chemically altered, its reactive potential stored within another molecule, like a battery waiting to be discharged. It's a story of chemistry, not alchemy. The process involves reactive oxygen species, unstable molecules containing oxygen that can bond with minerals like pyrite or with organic matter. Think of it this way. A log of wood and a blazing fire are both made of the same basic carbon compounds, but they exist in vastly different states of energy. The log is potential energy, stable and stored. The fire is kinetic energy, active and transformative. Dark oxygen is like the log. It's a stable, stored form of oxidizing power locked within the Earth's crust and sediments. The microbes that use it are the spark, unlocking that potential energy to fuel their own metabolic fires in the absence of any other energy source. So, a hidden chemical process allows microbes to live in mud. Why should that matter to anyone besides a few curious scientists? It matters because the smallest engines can drive the largest planetary changes. The discovery of dark oxygen has two profound implications that affect us all. One for the story of life itself, and another for the future of our global climate. First, it fundamentally rewrites the rules for where life can exist. For generations, the astrobiological mantra has been follow the water. But dark oxygen suggests we should also follow the chemistry. It expands the definition of a habitable environment, both on Earth and beyond. Imagine searching for life on Mars or on Europa, Jupiter's icy moon. We've long focused on finding signs of liquid water and organic molecules. Now, we have another critical ingredient to look for: minerals and conditions that could support the formation of dark oxygen. If life on Earth has evolved to use this hidden energy source, could life elsewhere have done the same? Perhaps beneath the rusty Martian soil, or within the dark subsurface ocean of Europa, there are microbes breathing not free oxygen, but oxygen locked away in minerals, powered by geological rather than solar energy. Closer to home, dark oxygen has a direct and urgent relevance to our changing climate. The vast stores of carbon locked in permafrost and wetlands have been relatively stable because the lack of free oxygen slowed decomposition. But if microbes can access dark oxygen as these environments warm and thaw, they could begin consuming that ancient carbon at a much faster rate. This process would release enormous quantities of carbon dioxide and methane into the atmosphere. Dark oxygen could act as an accelerator for climate change, a hidden feedback loop that might make warming happen faster than current models predict. Understanding this process is not just academic, it's a planetary imperative. Scientists are racing to quantify how much dark oxygen might be produced in these sensitive ecosystems and how it could affect greenhouse gas emissions. By incorporating this pathway into climate models, we can create a more accurate picture of the future. The quiet breathing of microbes in the dark mud could have a loud voice in our planet's destiny. It's a reminder that in a complex, interconnected Earth, there are no small parts. Every hidden process matters. What the discovery of dark oxygen truly gives us is a dose of humility, a cosmic reminder that our perspective is limited. The universe is always more clever than we are. For so long, we saw the world in a simple duality, the sunlit world of the living, the dark, dead abyss. We now see that this was a failure of imagination, not a failure of nature. Life is a tenacious and resourceful force, and it has found a way to harness energy from the very rocks and sediments of the planet itself. The demarcation between the living, the non-living, the active, the inert has become wonderfully, beautifully blurred. This new knowledge equips us with a sharper lens for looking at our own planet. We can now understand ecosystems not just by what we see on the surface, but by the hidden chemical reactions occurring deep beneath. This has practical applications, from managing agricultural soils to predicting the stability of wetlands and coastlines. As we learn more about the microbial communities that utilize dark oxygen, we may even discover new biotechnologies, perhaps new ways to clean up pollutants or generate energy. The most fundamental scientific discoveries often lead to the most transformative technologies, and this one is brimming with potential that we are only just beginning to grasp. The journey forward is one of meticulous exploration. Scientists will continue to venture into the planet's dark corners, drilling into the seafloor, sampling Arctic permafrost, and sending probes into the deepest caves. Armed with new questions, they will use advanced chemical sensors and DNA sequencing to map these hidden ecosystems and untangle the complex metabolisms of the microbes that call them home. In laboratories, they will recreate these extreme conditions to test their hypotheses and watch these cryptic chemical reactions unfold in real time. Each experiment, each data point. So, what is the ultimate takeaway? It is this: remain curious. The universe is under no obligation to make sense to you, but it always rewards those who ask questions. Dark oxygen is a perfect example of a mystery that was hiding in plain sight, waiting for us to develop the right tools and the right mindset to see it. It teaches us that there are still fundamental discoveries to be made right here on Earth, secrets locked in the mud beneath our feet. So, the next time you look at a handful of soil or gaze out over the ocean, remember the unseen world bustling with activity in the dark. Keep looking, keep wondering, and never stop exploring. The cosmos awaits.